In this video lecture, I shall quickly cover a topic in module 3 because it may be useful for the online test. Okay. Then later I will come to module 2 and discuss about the stick diagrams. Okay. Now, the first topic in this here is the scaling parameters. Okay, and the scaling factor for various device parameters. Now, generally, the word scaling is to increase or decrease the dimensions. Okay, it's a very general word, but in VLSI, the scaling is always meant for scaling down. Okay, so decreasing the parameters. Okay, and it has got lot of advantages as well as what we call it as figure of merits. Okay, the first one is it leads to minimum feature size. Okay, so it means the size of the transistor, interconnection and other components get decreased. So this leads to more number of gates on a single chip. Because of the decrease in the transistor size and the interconnections, the power consumption and the dissipation decreases, the maximum operational frequency increases, the die size is reduced. So you can have more number of dies on a single wafer. The production cost decreases. Okay, the power distribution decreases. The only disadvantage is that the current density. Okay, so the current flowing per unit area increases. That too when you consider this as a whole. Okay, now coming to the scaling models, we have basically only two scaling models. One is constant electric field and the constant voltage scaling. In the constant electric field, the electric field will be constant and all other parameters are scaled down. Whereas in constant voltage scaling, the voltage will be kept constant and all other parameters will be scaled down. In combined constant field and voltage, both the dimensions scale with the different scaling factors. Okay, and whatever the equations we derive for different scaling parameters, that will be based on this combined constant field and constant voltage scale. Okay, later we can convert it into constant electric field and constant voltage scaling parameters. Okay, now the scaling there are two basically scaling factors, that is alpha and beta. The scaling factor beta, it is basically used for as a scaling factor for supply voltage. Okay, and gate oxide thickness. Gate oxide thickness, it is denoted as D in some textbooks, and in some textbook it is denoted as Tox. Okay, so for supply voltage and gate oxide thickness, the scaling factor used is beta. And for all other dimensions, whether they are horizontal or vertical, the scaling factor is alpha. Okay, now this scaling factor cannot be any arbitrary value. Okay, the value for alpha and beta is carefully assigned later. Okay, now this is a 3D diagram of a N MOSFET. Okay, wherein it is scaled down. As you can see, the length of the channel, the width of the channel and the thickness of the channel, it has been scaled all by alpha. Okay, and the gate oxide thickness, as we have mentioned, it will be scaled by a factor of beta. Okay, so there may be a question, explain the scaled version of a MOSFET. So you should draw this 3D diagram. Okay, so this is this entire substrate upon which you have this silicon dioxide layer. Upon this you have the polysilicon, which is a conducting layer, and the source and the drain have been extended. Okay, now I shall stop here. So in the next lecture we shall see the scaling factor for various